Hello, hope you're having a great day so far. We're continuing our conversation about covalent bonding, and today we're going to talk about hybridization. So when you hear the word hybrid or hybridization, what does that mean to you? Well, hybrid means mix. Hybridization means mixing. So you think like hybrid cars. That means they run on both a mix of electricity and also gas. So hybrid means mix. And in chemistry, hybridization or hybrid means mixing of orbitals. Remember, orbitals are areas where there's a high probability of finding electrons there, and each orbital takes up to 2 electrons in there. And so these orbitals can mix together when the substances are covalently bonded. So hybridization is mixing of orbitals. So let's look at CH4. CH4 is methane gas, natural gas. And let's take a look at what that looks like. So carbon has 4 valence electrons, right? And if you remember, its electron configuration is 1s2, 2s2, 2p2. So these are your valence electrons right here. 2 are in the 2s, so this is the s orbital, right? And then you have 3p orbitals right here. And if you were to draw the Aufbau diagrams, there's your s with the 2 electrons, and then the p1 and 2, right? So the way that it is right now, I can't really bond 4 hydrogens, right? There's nothing here to bond with the 4th hydrogen. So what happens is we put the electrons here, right, so that we can bond to 4 hydrogens. So no problem, maybe one of the electrons just in the S went into the P or something like that, right? You remember the S looks like a sphere. The P orbitals look like dumbbells. So we'd expect that, the electron that's here, one of them would look like a sphere and 3 of them would look like dumbbells. In reality, when they checked CH4, it seemed like all these orbitals looked kind of like this. They kind of looked like a balloon almost. It's like a mix between S and P. It's not really a sphere. It's not really a dumbbell. That's kind of a mix. So they said, oh, looks like these orbitals mixed together. And it turned out that all 4 of these orbitals looked like that. So all 4 of the orbitals mixed together, and they said, oh, it looks like there's an s orbital and 3p orbitals mixing together, so let's call that sp3, because these 4 orbitals are a mix of 1 part s and 3 parts p. So it turns out that this hybridization, this mixing of orbitals, happens all the time. So let's draw these structures and try to figure out what the hybridization is. So let's draw them first. Go ahead and pause the video and try to draw them and then check. See if you got them right. All right, so welcome back. So let's take a look at these. And as you're drawing them, you probably noticed that there's lots of lone pairs. You also probably noticed a couple that didn't really make sense to you, right? Those last two. Let's go over each of them. So to figure out the hybridization, what you do is you look at your Lewis dot structure. You pick your central atom. Hybridization is for each individual atom. So if they're both the same, like H2, then you just pick one of them. It doesn't really matter which one. So let's pick this hydrogen right here. Okay, so you count how many areas of electrons are around. Whether these electrons are in lone pairs or in bonds, it doesn't really matter. So count how many areas of electrons are there. So it looks like around this hydrogen, there's only one area of electrons. The areas of electrons will represent how many orbitals were mixed together. And so remember the orbitals, there's one s orbital, there are 3 p orbitals, there are 5 d orbitals, and there are 7 f orbitals, right? So it looks like we only have one orbital, and so that's just going to be an s. That's not really a hybrid, so H2 doesn't really have hybridization. Let's look at N2. Again, both nitrogens are equal here, so it doesn't matter which one you pick. I'm going to go ahead and pick this nitrogen. And you count how many areas of electrons are around it. So it looks like this is an area of electrons, right? And then this is another area of electrons. The fact that it's a triple bond doesn't matter. It's still one area of electrons. They're all in one area, right? So it looks like there's a total of 2 areas of electrons around that nitrogen. That tells you there are 2 orbitals that mixed together. The first one's always an s, and then the second one is going to be a p. So the hybrid is what we call sp hybrid. It's a hybrid of 2 orbitals, 1 part s, 1 part p. Let's look at CH2O. So it looks like this. This one has a central atom. That carbon is your central atom. So let's count how many areas of electrons are around that central atom. So it looks like there's 1, 2, 3 areas of electrons around that carbon. So 3 areas of electrons tells us there are 3 orbitals that mix together. The first one's always an s, and then 2 more that are p's. So sp2. sp2 hybrid. Let's look at the ammonia, the NH3. So here the nitrogen is our central atom, and let's count how many areas of electrons are around that nitrogen. So there's an area of electrons, there is 1, there is 1, and there's 1. That's a total of 4 areas of electrons. That means 4 orbitals mixed together. 1 is an s, and then the other 3 are p's. So sp3. Okay, let's look at PCl5. You might have been confused by PCl5 and SF6, right? It doesn't really make much sense because look at that phosphorus. It has 10 electrons around it. It's more than an octet. Well, it turns out in some situations that happens. PCl5 and SF6 are molecules that actually exist. And so, it just happens. Now, how would you know? Well, there's no way to bond phosphorus to 5 chlorines unless you have 5 bonds around the phosphorus, which would make it have 10 electrons. So there's no other way to draw it, and so you will know just because of that. So the phosphorus is our central atom. Let's count how many areas of electrons are around that central atom. So there's 1, 2, 3, 4, 5. So 5 orbitals mixed together. Let's see, 1 is an s. We can only have 1 s, right? Then how many p's can we have? We can have 3 p's, right? There's only 3 p orbitals. But we said there's 5 orbitals. So 1 s, 3 p's. What's the other one? It has to be a d. So it's sp3d. Okay, SF6. Again, a weird one. SF6 is actually a pretty cool gas. It's a very, very dense gas. It's almost the opposite of helium. You know how like if you inhale helium, your voice gets really, really high? If you were to inhale SF6, your voice would get really, really deep and really, really low. If you look at Schoology, the folder that says fun videos, I have a couple of fun videos about sulfur hexafluoride. There's a video where from Big Bang Theory, where Leonard inhales it, and he has a very thick or deep voice. There's another cute video of two kids doing a kind of a science fair project where they show sulfur hexafluoride, and they show that it's actually more dense than aluminum. It's pretty cool, so I recommend that you watch those videos. Anyway, sulfur hexafluoride, the central atom, the atom that's in the middle is sulfur, and let's count how many areas of electrons are around that sulfur. 1, 2, 3, 4, 5, 6. So 6 orbitals need to mix. 1s, we can have up to 3 p's, so that takes care of 4 of them. Need 2 more, so D2. So sp3d2. So whenever you need to figure out the hybridization, you draw the Lewis dot structure, look at your central atom, count how many groups of electrons are around your central atom. That tells you how many orbitals will mix together. You can only have up to 1s, 3 p's, 5 d's, and 7 f's. One quick note. So these hybridizations right here where there's a D involved. A few years back, maybe about, I don't know, 8 or 9 years ago, they proved that the d orbitals don't actually mix together with the s's and the p's, but they haven't really come up with any research to explain what is actually happening. And so in a lot of college courses, they are still teaching these hybridizations with the d orbitals. And so that's why I'm teaching them in this class. Hopefully by the time you get to college, they would have figured it out and changed the textbooks. But for now, I'm just going to teach it to you. But know that that's kind of like a little bit of a lie. It's not really entirely true. But because they're teaching it in college, I'm just going to continue to teach it until they come up with a different theory. So, again, to do the hybridization, just draw your Lewis dot structure, count up how many areas of electrons are in your central atom, and that will tell you how many orbitals are mixing together.